Hello, my name is Mohammad Mehdi Hosseini. I'm a PhD candidate in electrical and computer engineering at the University of Utah. Here I'm about to present our work on computationally efficient formulations for fault isolation and service restoration in distribution grids. The main motivation behind our work was that although many methods are available for distribution system reconfiguration, there is a lack of efficient methods for automatic fault isolation and service restoration, where there are limited number of remotely accessible or automatic switches in the system. The few available methods use too many binary variables and therefore are not efficient for real-time operation. In this work, we are introducing two mixed integer programming models for fault isolation and service restoration that only use one set of binary variables, and as a result, is fast enough for real-time operation. Here, the mathematical model to find the solution for fault isolation and service restoration problem is briefly explained. In this problem, we have a limited number of automatic switches as shown in figure on the left. And on the right is our suggested formulation, which is based on conventional branch flow model, where we want to minimize the cost of operation subject to line flow, power balance, and voltage drop limits. These limits are inherently nonlinear, but can be approximated to linear or quadratic forms. Then we add a new set of formulations numbered from 1 to 6, where we introduce a new variable called the EIJ, which shows the energy flow direction from node I to J. If there is a fault on line IJ or other lines that are connected to IJ, variable EIJ is required to be 0, and that is how we model the fault isolation requirement in our model. The model is tested on 32-bus and 123-bus distribution test systems, and the results of 123-bus test system is shown here. As shown in the table, both models are able to find the near optimal switching operation to isolate the fault and restore the service. Comparison of the computational time shows that the linear model is way more efficient and can find near optimal solutions in a fraction of a second. In the bottom figure, the switching accuracy and computational time of the developed model is compared with other available methods, which indicate that the linear model can find the solution in almost real time in a relatively large 123-bus test system. In conclusion, we have developed linear and quadratic constraint models for fault isolation and service restoration for distribution systems with limited number of remotely accessible switches. The linear model was shown to be the fastest as compared to the QC model and other available methods, which makes it ideal for real-time operation. And finally, the developed model can be utilized for distribution automation planning to find the optimal type and location of automatic devices. Thank you very much.